Yeah, xCORE delivers high processing capabilities across four different classes, so control processing, DSP, AI, and I/O processing on any one of its processing elements, and it does so in a manner that is entirely predictable.
Hey everybody, Dave Limburg in Hong Kong with a new episode of THD Podcast. Thanks for tuning in. Today we have the CEO of Xmos coming to tell us about their generative system on chips. It's a new category of semiconductor to integrate AI directly into the system level hardware. So we're going to find out about that. I think there was a strange history between Xmos and a company I used to work for, so I'm going to ask a question about that. But without delay, let's give a shout out to our sponsor, the Alti Association, great industry networking association. They're going to be at Axpona in Chicago and High End in Vienna coming up in the next few months. So please check them out. And also the Audio Express. Please subscribe to their publication. So without delay, let's say hello. So we have Simon in Sendai, Japan,
Hey, good morning, good
and
evening.
Mark in the UK. Good.
Hi, David.
Good morning, Mark.
Hi, Simon. Thanks for having me.
Right.
All right. So let's get into pitching people on this generative system on chips. Tell them what it's all about.
Okay, cool. Let me just I'll share a presentation here. So we've been Xmos has been in the world a semiconductor company for about 20 years now, and we've sold over 40 million devices, many of which have been sold into audio applications. But the underlying sort of philosophy of the company, the vision of the company, was to develop off-the-shelf silicon platforms that software engineers could tailor into many different applications simply by downloading different software images. And the generative SoC term really reflects the combination of that super flexible platform, silicon platform, and the latest generation of development tools, which are based on large language models and generative design techniques. And it's a very sort of exciting combination for us because as a relatively small company, as a sort of a scale-up business over the last few years, we've been trying to sort of fight for our share of our mind share amongst some real giants. I mean, if you go back, 30 years or more, people were developing ASICs, and that was a much more sort of heterogeneous world in which many different vendors, many different design teams, and supply chain contributors all sort of contributed to some fairly specific and bespoke solutions for very specific problems. But those problems were quite large, generally speaking, quite big enough to justify the expenditure and stable enough to accommodate the fact that these things take 3 or 4 years to develop. And then of course ARM came along and built and this concept of an SoC developed, which is partially programmable but wrapped in a collar of hardware that is more application specific. So these were sort of semi-targeted. And again, they suffer from similar challenges. They're a little bit less flexible. They're targeted roughly towards certain applications, but they've been hugely successful at delivering on a whole variety of different things, including what we call, or what we have called in this period, the Internet of Things, which is not really one market. It's a huge array of different applications, a sum of niches, if you like. And these ARM-based SoCs have been, somewhat successful in that capacity. Xmos's vision was of an evolved market, a market that is even more dynamic, even more fragmented than the markets that can be addressed with ARM-based SoCs, by virtue of the fact that, in our experience of working in the semiconductor space, customers are becoming more and more, their appetite for faster market solutions is becoming, more and more voracious. So even things like ARM-based SoCs, where you've, maybe you've got the right solution of components, but frequently you haven't. Those are becoming too slow. We really need to be able to innovate hardware behavior at the speed of software, and that was the original thesis of Xmos, 20 years ago. And this combination of Xmos platform, which has these capabilities that enable software engineers to do hardware-like things, is really enabled by generative tool flows, and that's where this idea of GenSOC came along. to brand our existing technology, which has been very strongly proven in the market, particularly in audio applications, but to sort of to show this new way of building systems, not just on Xmos technology, but a way of building systems in the future. And the sort of thesis here was, and I tend to use an analogy, which is when you're learning to drive a car, you don't need to know about how a four-stroke engine works, right? It just works. It delivers properties. It delivers motion. The steering rack delivers steering. Controls. Those controls, they deliver properties that you require of a car and you require of every car, but you don't need to know how they're being done. And what we've been doing in those previous generations is make it very explicit to an application developer how that application is being delivered. And we've kind of got new.
Hey, can we just jump back one slide for a sec? So we're talking about the difference between like ARM SoC and what you're doing. And what I just wanted to check, what you're talking about is an ARM SoC vendor from NXP or whatever. They come along and they decide we're going to build in all of these peripherals. So you've got a processing core, but then we're going to attach a whole bunch of different peripherals, and you have to go and figure out the registers and everything to do I2C, I2S, or UART, and all this kind of thing. That's the difference that you're describing. Is that you don't. You're not working in the space where you've got a set of peripherals that you're trying to interface with.
Well, so yeah, it's a great point. So I guess maybe I'll step back, if I may, one point, because it becomes important later on. So every system in the world has hard real-time requirements, and they have those hard real-time requirements because in order to interface to anything else, you've got to meet deadlines, typically on I/O protocols, for example. And the only way to do that in an ARM-based SoC is to actually implement those features in hardware. So with an ARM-based SoC, you'll have this programmable core, maybe more than one core, and you'll have a collar of fixed function gates, which are implementing the interfaces to the outside world that were envisioned by the product planner or the product manager 3 or 4 years ago, maybe longer, as being sufficient and appropriate for the markets that they were originally targeting. So we've thrown that idea away. So essentially, we have a platform that you can take off the shelf that has the hard real-time properties that normally you can only get in gates in software. So now you can download libraries that behave like hardware. They have the hard real-time properties that historically you'd have had to have got out of doing a tape out, which would have cost you millions and taken years. So that's really where the fundamental kind of velocity comes from. And it's also about, design communities as well. In the space that we operate in, which is typically in embedded systems nowadays, people talk a lot about physical AI and agentic AI, but the systems at the edge of the networks, if you will. Those are very, they're cost constrained. I mean, typically that's at the top of the list of priorities. But increasingly they're constrained by very fast time to market. First mover advantage is all important, and power as well. And the community that is designing those systems, primarily software engineers. The FPGA cohort has moved into different domains. In the early stages of FPGA design. It was a sort of very much a platform technology, but as communications and more recently AI has become important, those kinds of engineers you don't tend to find in companies building these kinds of systems. So the only way to deliver this benefit is through the flows that used by software engineers. And actually, that's what we've been doing for many years. That's how we've sold 40 million of these things already. But I think the idea that you can start to do this using generative approaches really does open up the possibilities again to a wider community of creatives.
Can you just elaborate a little bit on what's meant by generative approaches?
Yeah, I'll talk about this a bit later. In fact, if I can move on, this next slide really starts to talk about it. So the idea is, again, the generative aspect will come to a bit later. But the idea is that we should allow people that are audio engineers. We should allow people that are robotics engineers. We should allow people that are that work in images to articulate their systems in the language of their application. We shouldn't be asking those kinds of people to understand the mechanisms by which semiconductor companies deliver the properties that they need to run their system. So the idea of a generative approach is in the same way that for an enterprise system, we might prompt program, we might use vibe coding, is to bring that into the world of embedded systems where not only have you got functional requirements, but typically you've got these very strong hard real-time requirements as well. And the idea is essentially I guess lifting the application engineer out of that world is one way of putting it. But actually, I would prefer to say let's leave the application specialists, let's leave those sector specialists talking about how they want to build applications in the language of their application, rather than having to say, oh, I'm going to deploy this, this control function on the ARM processor, and I'm going to lift this DSP function and run it on the hi-fi because that it needs a little bit more performance. And I've got some AI, so I'm going to have to do that on this MPU over here. Understanding that all of those details of the platform shouldn't be necessary for people to deliver value into their own sort of ecosystem. So the sort of challenge here is how do we lift our development community out of that detail, that level of unnecessary detail, and really liberate them to just sort of express themselves in the language of their application. And vibe coding in the enterprise really does allow that. It allows people to sort of essentially use natural language to describe systems. But there are significant challenges when you're moving that kind of thing, that kind of technique onto embedded platforms where resources are highly constrained, and you have these not just functional constraints, but also hard real-time constraints that you've got to meet in order for systems to work. And noting in some cases that these systems are safety critical as well. So these things they can have some serious consequences if things don't quite work out. So
it's kind of like it's a tools platform that allows you just to talk in natural language and then map those applications onto the different like whether it's IO, DSP, etc.
Mm-hmm. That's right. So I've got a couple of slides to talk about the sort of the underlying hardware, and then we can come back to that and see and sort of build up and see how the whole thing fits together. So the xCORE architecture, I've got a couple of slides. This is about as abstract as an xCORE architectural block diagram looks. Essentially, we have it's a homogeneous multi-processing architecture because. And this is necessary because if I go back to that point, that value of hard real-time behavior that we deliver, there's no way that you can deliver that kind of single-digit nanosecond resolution on timing by sharing a processor pipeline, right? You have to be able to dedicate resources to that kind of to deliver on that level of performance. But at the same time, at the other end of the spectrum, you might have applications code that is not timing critical. But the key thing is that at the hardware level, in order to deliver real time through a software design flow, you have to make some very, very innovative decisions about what the hardware looks like that give you that level of timing accuracy. And then if you want to, in the building your system, if you want to give that away, that's fine. The point is that at the hardware level, it needs to deliver it. Otherwise, you can't deliver on the flexibility of building the whole system, including all of the bits, the hardware IOs, for example, that might have been otherwise implemented in gates. So the xCORE delivers high processing capabilities across 4 different classes: so control processing, DSP, AI, and IO processing on any one of its processing elements, and it does so in a manner that is entirely predictable. And those are the properties, the key core properties that xCORE delivers that enables us to build these tools abstractions on top. So that's the sort of primary sort of properties of the xCORE architecture that is quite novel.
I think this is the part where I used to work for a company called 11 Engineering that made a multi-hardware threaded processor, and I remember people telling us dumb business idiots that there's only one other company in the world that does a hardware multi-threaded processor, and it's Xmos. So finally get to meet the guys. Okay,
there you go. Yeah, and frankly, that architecture has served us extremely well. The ability to dedicate individual processing elements to certain tasks, not just in a static way, but also in a dynamic way. has enabled us to be extremely silicon efficient for certain types of solutions. So, we one of the areas that we obviously, we if you like, from a commercial perspective, we grew up in audio, but we've continued to build on that into, from audio to audio DSP to audio AI to voice AI and now to imaging AI. And one of the applications that uses voice AI and imaging AI is access control. So these smart locks, and in those cases, you can actually flip from initially being imaging AI. So you're looking for somebody, you're looking for a person approaching the doorbell, for example. But once you figure out that they're there and they're standing in front of the doorbell, you can flip to a voice control solution. And that's those kinds of things make the overall solution extremely efficient, because you've essentially used the same silicon for two quite different things that is imperceptible to the user. It's the same user experience, but may have halved the cost of the bill of materials, for example. So this kind of not just the static flexibility, if you like, where we can do lots and lots of different types of systems, but the dynamic flexibility is extremely efficient and useful in many different systems. So the other thing I haven't mentioned is, so we have two tiles. We have hardware threading, as you correctly pointed out. Each one of those elements is capable of doing all of those different classes of processing. But we also have this switch, which allows our systems to scale. So many of our customers actually use multiple chips, and that's either because they're using the same code base across a portfolio of products, and they want to be able to reuse that software, but they need more resources, and the xCORE architecture allows you to put down two chips and have what appears to be one chip with twice as much resource. So it's that level of scalability has been built in as well. So and of course, critically, and this is the absolute cornerstone of our technology, is all of that scalability. It doesn't give away the real time performance. Nothing does. So that's the sort of the underlying sort of architectural guarantee that we always preserve no matter what we do. So that's the sort of
So using the term processing element as opposed to core, is a distinction?
Yeah, good observation. I mean, so in principle, we have an architecture which has a lot of properties, real time and parallelism and scalability and so on. In principle, it could be implemented in a few different ways. You could do it with a genuine multi-core solution. You could do it with a multi-threading solution, as long as it retains those timing properties. We actually do it with a combination of things. So there's two tiles here. Within the tiles, we use multi-threading, and obviously between the tiles, that's genuine, execution parallelism. There are other ways of skinning the cat. The next slide that I'll show you, if I'll just flip forward, kind of exposes the fact that we use hardware threads in those tiles to achieve silicon efficient, to achieve the right level of performance and silicon efficiency that our customers need. So this is actually a representation of our 4th generation chip, which is just back from fab. And this is a RISC-V based device. So each one of those hardware threads looks like an individual RISC-V processor with extensions for the other classes of processing. But it works in essentially the same way. It's a underlying platform with multiple processing elements and 4 classes of processing, and obviously all those real-time guarantees as well. So this is a sort of an embodiment of that architecture, which has all of the system services functions and so on. As you can see in the bottom, there's things like system PLLs. Typically, our devices run at sort of 800 megahertz, so we need a system PLL. We have application PLLs, which are useful, particularly in things like audio, things like power and resets and security keys, debug. But also, there's a couple of things on there that are somewhat application specific, because they are analog or high-speed serial interfaces. So USB 2, for example, a lot of our audio customers, in fact, many of our customers in general, use USB. And for low-cost imaging, we have a MIPI interface on there as well. But generally speaking, when we're making architectural and silicon design decisions, our default is always, can we do that in software? Because if we can do it in software, that preserves the silicon flexibility it preserves that silicon, if you like, to be used for any number of different things, and that gives us that level of silicon efficiency that our customers really value. Mm-hmm. So that's the underlying kind of architecture that it has been with us actually right from the very beginning, and this architecture has been very, very well proven.
Okay.
In terms of performance, and just to sort of, this is a sort of a calibration point, really. The architecture itself, back in the day, we built a huge array of these things, and we actually were doing some sort of more what you might consider to be data center type kind of modeling, just to prove the fact that you could build big systems. But our wheelhouse has been, as I say, deeply embedded. I think the market characteristics, the diversity, the dynamism, the sort of the time to market pressure, it really sort of resonates with the properties of our technology, with the flexibility of the technology, and the fact that you can program it using you can program hardware like things using software. So we chose a performance envelope, if you like, that works well in that space, and back over 10 years ago now, it became apparent that the performance envelope that we were delivering was particularly suited towards audio type workloads now, and that's really where the company started its commercial development, even though the underlying technology was general purpose. As a small business, we pushed ourselves, we have to be very focused from a commercial perspective, and we pushed ourselves. Having identified an opportunity in the audio space, we used that as our beachhead for commercial growth. And essentially, the properties of the architecture have stayed quite stable. We've used different process nodes along the journey to deliver more capabilities, more performance, more memory, for example, in a similar footprint at a similar cost point, rather than using, for example, scaling up and making the device more expensive and less accessible to our core market. Mm-hmm. So xCORE AI or xCORE 300 is the device we're selling most of now, and it's essentially somewhat superior to xCORE 200 in every way. The key difference between xCORE 200 and xCORE AI is a vector unit in the execution part of the processor, which allows us to do AI workloads and including bitwise AI workloads and 8-bit resolutions. But also the vector unit is also capable of doing 32-bit resolutions with for accelerating parallel DSP workloads as well. So we find what's
a vector unit?
Oh, okay. So if you look at a classic sort of processor pipeline, it has a pipeline that is divided into various different stages that instructions travel down with some stages being dedicated towards reading instructions, reading data, other stages towards execution, and later stages towards writing that back. So that's a sort of a classic pipeline. Alongside that, in the xCORE AI, we actually have a vector unit, which is essentially operates with a single instruction over multiple data. So it'll do a single operation over a group of 8 32-bit registers, for example. So it operates in parallel over a larger data set. And when you're executing things like AI workloads and some DSP workloads, you get a tremendous amount of acceleration from that. So our vector unit, you can operate on 32-bit quantizations. You can operate on 8 bits and 1 bit if you want to do binarized neural networks. And that gives us as I say, that operates in parallel with the if you like the traditional pipeline, and gives us a significant uplift in performance in some of these sort of more mathematically intensive applications like DSP and AI.
Thanks.
So, in terms of what this allows you to do, this is an audio solution. So this is one of our somewhat earlier customers, actually. they had a solution that was already shipping, that they built, from multiple vendors' products, and they were able on their own to take all those functions and deploy them in a single XMOS device. So the real motivation here actually wasn't in this case bill of materials reduction. It was time to market, because building with 6 different chips, 4 different classes of chips on a board is complex. Their actual motivation was to build their solution very quickly. But at the same time, because we're taking 6 discrete devices and moving them onto a single one, there are quite significant system economies available. So we really measure ourselves on 2 axes. We want to get our customers into market dramatically quickly, but also, we want to be able to save them money, save them bill of materials cost at the system level, and we'll achieve that by popping out, looking at not just at replacing individual chips, but looking at systems as a whole, trying to find other aspects of a system to integrate onto our platform, and we've been really successful at doing that.
Okay. So
this was an audio solution, as you might be able to tell by some of these sort of physical interfaces you can see there. But we're present in many different things. Audio, as I say, that was our beachhead market. We've gone from audio connectivity to audio DSP, so that's enabled a lot of areas like conferencing and the microphones, live recording equipment, things like that. But also, audio is now everywhere, right? So not only have we, diversified into other types of time series processing, but audio is finding its way into all sorts of things. Not because of traditional reasons, not because of audio as a human experience, but as audio as an input to machine learning. So you find, audio event detection, for example, gunshot detection, glass break detection, loud noise detection in factory context for safety purposes. All of those, even in smart farming, there are audio applications now. So audio is very much a capability and not a market, and we're very happy to see it's moved across into many quite unsuspecting areas. But at the same time, we're also involved on the physical side. So robotics, e-bikes, all of those kinds of those things where real-time control is highly valued. You'll find Xmos solutions are present in those areas. So the market for our technology is huge. And we're really frequently really excited about where things pop up, and where xCORE technology pops up, and it sometimes pops up in the most unexpected of places, and it's great to see what customers can achieve.
Yeah, and definitely the ability to use this kind of software approach development versus, I remember with the other processor, it was written in assembly, so nobody could develop on that platform. But if you guys make it easy for developers, you could find it in many places, as you're telling us now.
Yeah, and that is a really important strategic decision that you have to make. Is, are you going to open your tools to your customers and partners? Because the implications of that are quite broad. For us, it was always the intention, because we thought, as a business, and I still believe this, that we could never capture the creativity of the community. That's never going to happen. The best thing to do is to try and facilitate it. And I think as computational classes have increased, so from control processing, DSP to AI, that becomes more and more the case. The amount of different types of AI algorithm or AI model in the world is staggering. Even for a particular function, there'll be different language for voice processing, for example, different languages and dialects. There is a huge number of models that one would need in order just to deliver a single solution across a global ecosystem. So I think the key thing for our company, or at least the decision that we made, and I think we're very happy with it, is build a really good set of tools and let other people let other people express themselves. Now, we've obviously, we project ourselves into certain markets with reference designs and so on. Our USB audio reference design has built an enormous reputation for robustness and quality. But you know, our DNA, if you like, is to enable people outside our business to have that level of creativity as well. And that's been, for example, the robot arm you can see on this slide.
Mm-hmm.
That was built from pretty elemental libraries and tools supplied by us. That was a tremendous amount of innovation that our partner did there, understanding the value of the real-time performance of our system. The Ricci robot, which is just below it, actually was developed quite independently of Xmos, and we were very, you know, that was one of the stars of the show at CES. Jensen Huang presented the Ricci robot during his keynote speech, and it's just genuinely delightful. I mean, it really is. You know, I've never seen a robot that is quite so endearing as Ricci, and you know, I'm really excited about what people are going to be able to do with that. And that's the lovely thing about Xmos. You know, these solutions pop up in all sorts of different places and all sorts of different use cases. And it's just great to see people's, you know, innovation.
Right. Yeah, that's cool.
Yeah. So I'm going to start talking a little bit more about the tools. We'll come back to the tools. I'm going to flip past. Just actually this is more of an audio centric slide, with sort of tipping my cap to the audience a little bit. But so, I don't know if you know Sam Inglis at Sound on Sound, but he made a very kind quote to us in an article in 2024, in which he said that essentially that the Xmos brand was you know, ranking right up there with Apple and Sennheiser and some of the real, you know, some of the greats in the sort of professional audio space, which, you know, it's just lovely to see. I mean, I think the Xmos team have done a fantastic job of creating that software stack and obviously leveraging the properties of the underlying hardware. And our customers have done an awesome job of building great products with it. That was just lovely to see. So the GenSOC design flow. So let me just focus for a moment on the way that the embedded systems are normally built. So normally, with an ARM-based SoC, for example, you've got a C compiler. You'll have a number of libraries that drive peripherals, which are typically implemented in hardware. You'll probably have a real-time operating system because you've got more than one thing that you want to be doing at a time. And you'll have this sort of, you know, this compilation suite that will exist. It will contain, you know, compilers, it will contain debuggers, loaders, linkers, all sorts of kind of off-the-shelf, well, maybe not off-the-shelf tools, but run-of-the-mill tools, if you like, you know, expected hygiene factor type tools that embedded systems expect to see. And our goal as a vendor of very innovative hardware was, let's just replicate that, because we don't want to be re-educating the embedded community on how to do things. Mm-hmm. Right? That was not our mission. Our mission was to deliver this level of flexibility, hardware-like behavior through a traditional sort of software development flow. Generative AI has changed that. You know, the challenge for us with that was we couldn't deliver on that mission without exposing our customers to understanding some of the details of the underlying architecture. And fundamentally, we were bringing a different architecture to market. So there was an educational step there. There was a lack of familiarity, and that was a hump that we needed to guide our customers past. With generative AI and with this idea that actually customers shouldn't need to understand what the underlying platform looks like. You know, it's a fallacy that an ARM-based SoC is easy to use. It's not. It's just familiar. And people shouldn't need to know it, shouldn't need to understand its details. So how can we just pop people up into the application domain and have them describe their systems there? And this is the promise of generative AI. And essentially, it marries together the ability to do I'm going to call it vibe composition, because it's not quite vibe coding, and that relies upon the properties of the underlying platform in order to deliver systems that are correct by design. So not just functionally correct, but timing correct in a manner that means that you could deploy at scale simply by continuing to describe systems at the abstract, at the application layer. So how does it do it? So we use a generative AI system that is essentially it's self-supervised learning on the web. So it learns how to build systems on the web. So you can you have a prompt. You can say, build me a motor control solution for a 3-axis motor control, 3-axis robot arm, and it will learn. It's learned from the web how to put those solutions together, and it will give you a very plausible block diagram of how to do that. So you have an application level block diagram. You then have some pre-built or pre-built, unit tested, pre-verified, characterized libraries, and underneath underneath the generative tools compiler, you have an understanding of the platform. The key thing is the understanding of the platform doesn't go all the way up to the customer. They don't need to know. There is this, what I've called here, a behavioral compilation step that understands the properties of the platform and understands how to deploy systems on it. And that enables you to basically to describe systems at an application level, and essentially hit compile, download, and you've got a system. You've built a chip. Essentially, you've built an SoC for your particular solution. So it's dramatically fast, right? So Xmos went from in the very early days, it went from trying to convert what was a 3 to 4 year ASIC flow into something that might take months for a software engineer. We've now gone from months down to I've been known to say months to minutes, and it really is quite, that is possible. You can create systems that would have taken months, even on xCORE, which is already an accelerated platform, and you can start to develop systems in minutes. So I'll pause there because just.
Is there going to be is there a barrier to entry for other people to develop similar tools and get that acceleration as well?
It's a great question, because everyone's talking about generative tools now, aren't they? I think the key thing to observe is that there are. I suppose I can answer that on two levels. When you're going from generative tools in the sort of enterprise domain, your constraints are far lower. So you've got typically more processing resource, more memory, perhaps a higher tolerance to variable timing, for example. It's a lot more of an unconstrained environment. When you start moving towards embedded systems, you have memory constraints, you've got processing performance constraints, you've got real-time constraints. So it's much more difficult to create a system that is correct by construction. You have these various different constraints compete with each other. You typically don't have a golden reference solution with which to train the outcome. So it becomes a little bit more difficult to get a perfect solution from a generative approach. And these things are changing all the time, as I'm sure you can imagine. But many companies with ARM-based SoCs are talking about generative solutions. GenSOC moves things forward quite a bit, actually. The GenSOC concept allows people to build. Well, first of all, you've got the underlying flexibility of the platform, which means that you can build systems that have got a completely unique properties, including the IOs, including all of the everything from edge to edge can be defined and refined by this generative approach. But also, you've got the timing determinism of the platform. So, from an abstract perspective, you can say, I know exactly how this thing's going to behave because I'm building it from these functional blocks that have certain properties, functional properties, but I also know exactly how it's going to time because I'm getting that guarantee from the underlying platform. So if I, for example, if I were to develop a solution for an ARM-based, ARM-based SoC for an ARM processor, yes, you could deploy a system that had multiple blocks onto that processor, and the RTOS would attempt to schedule them, but you'd have no real ability to reason about the timing because that ARM processor is going to be interrupted. You don't know what priority you're going to get from the RTOS. You don't know what else is running and what impact that's going to have. So you can't guarantee the timings. You can't get to the same solution. You can't generate an SoC. And that's the key point.
Okay.
Sorry, Mark, could you give an example of a hardware thing that you're implementing? Would we be saying, please implement a USB host controller that's capable of XYZ? Is this the kind of general?
Right, hold that thought, because
Okay.
let's see if we can actually do that live.
Okay.
So this is the flow. So essentially, at the top left, you've got the natural language aspect of it. So you're just going to write, I like this, this, and this. The generative tools essentially use a set of pre-configured libraries that describe functions. So the generative tools will put together a block diagram, and then it will use the sort of metadata relating to those components in order to put together a system that will deploy. And then the final stage is in that traditional compilation stage, where it takes all those blocks, compiles them, links them, and deploys them. So you can actually go. And if anyone wants to come to see us at Embedded World, you can see this running, live and use it yourself. But you can actually drop the system that you've just designed in natural language down onto the chip and listen to it in real time, and tune it, in fact, in real time. But the key thing is, it comes back to the properties of the platform. The key thing is not that you can do that. That's possible via a number of platforms, potentially with a little bit of smoke and mirrors constraining what's going on. But on the xCORE platform, the key thing is you can take it to scale, because you know what the properties of the platform are, and you know that guarantees the timing and functional behavior in all different use cases. So this is the tool looks like this. This is a karaoke system. I'll show you this one being built, but essentially it's a set of pre-verified libraries on the left, a block diagram that's completely at application level. So there's nothing in that block diagram that relates to the platform that it's going to run on. There's the ability to do hardware in the loop optimization of parameters, and there's this sort of natural language box in the bottom right hand corner where I can build the system. So it's the first iteration of generative, the generative SoC tools is audio centric, because that's our direction of that's where we've come from. So we're trying to enable those customers to build great systems comprising of DSP, AI, and all the sort of interfacing technology that we have. So I can show you that thing in action.
Okay.
So do you want to have a look?
Yes,
please.
All right. So this is the opening, the home screen, if you like, of the GenSOC tools. And as I say, this is targeted towards DSP. So there's a few regions here. On the left-hand side is a number of DSP elements. In the middle is the graphical user interface. And on the right-hand side, well, we'll see what happens on the top right-hand side in a moment. But on the bottom right-hand side, there's the ability to interact with a natural language interface. So if you want, you can build systems in a traditional way by sort of dragging and dropping. But we'll do something a little bit more interesting. So I'll ask for a karaoke system, for example, with a mic into it.
How about dual mic?
Yeah, we can try that. Well, let's do that. Let's do that second.
Okay.
It's gone away. So this is actually it's building a system level block diagram from unsupervised learning on the web, right? So it's basically gone away, and it's built a system level block diagram of a karaoke machine. It's platform agnostic. None of this stuff here is specific to xCORE at all. Interestingly, it's done some value adding things. So it's built reverb, and that gives me a good opportunity to put reverb on the microphone channel. That gives me a good opportunity to show you what happens in the top right hand corner. So if you click on any one of these blocks, you can tune it. And you can, if we were in the same room and I had a board plugged in, you could actually listen to the impact of changing some of these parameters in real time. Right. It's added ducking. It's added ducking as well, which it's sort of leant forward a little bit there. This is essentially ducks the music on your voice when you speak.
Okay.
So that's another feature. I'm gonna take your challenge there. And so this is in terms of velocity, this is just dramatically faster than building systems in a traditional way, and it's also as I say with a
right there you go.
with a system where you understand both the function and timing performance in tremendous detail, you can actually just deploy this and know that it's going to continue to work under all use cases. So you've now got a second microphone. Should we add an equalizer?
Yeah.
Oh, let me do something a little bit more interesting. I'll ask it for something that's not sufficiently descriptive. So I've asked for a crossover. Obviously, that's not enough information. So it's come back and asked me for what the crossover frequency looks like. Oops. Okay, so let's pick it out. There's a typo in there. So, I mean, as you can see, this in principle, we've just built a karaoke system. There's a build button at the top right-hand corner and a run button, which would have deployed it on hardware. And you're done. You're finished. Now, if you want to plug in your own blocks as well, because obviously one of the critical things that we get asked is, well, I've got an implementation of reverb that's second to none. I want to use mine, and then that obviously is also supported. So there's the ability to build container blocks that the AI, the generative tools can introduce into systems as well.
Right. Probably need a vocoder plug-in on the DSP to fix our awful voices as well.
Yeah. There's a pitch. We don't have a pitch corrector algorithm yet, but there has been some demand. Yeah.
Right.
But So the crossover filter's been added there as well. So yeah, I mean that hopefully gives you an idea. But I mean it's one of those things. It's so easy that you can sort of misinterpret it as being quite superficial. But you can actually deploy this system. You can actually create a binary from this and make hundreds of thousands of them, knowing that the underlying platform is going to protect the function and timing performance.
And also support, like especially with audio and pro audio, there's a lot of micro businesses that want very specific functionalities, and typically it'd be difficult to develop for small volume stuff. So this is very interesting.
Yeah, and there's nothing. Sorry, go on.
Yep. Anyway, so we've got the block diagram, and you can build and deploy it. How does this distribute across the 8 processing elements? How does it bind to IOs and this kind of
great question. So this is designed for a dev board. So the IO question is already answered because the chip's on the board. So
you've specified what my IO pins are to be used as. Yeah.
Yeah, so for if you're developing your own chip for your own board, then yes, those parameters will be you will define those parameters where the IOs are. That it will guide you as well. I mean, depending on which interface you're using, there may be a subset of the IOs that are available, different bit widths and so on, but it will guide you through that process. So the idea is that. I mean, I suppose allocating IOs is somewhat platform specific, but if you're going to build a board, you can't get away from doing that. That's a question and a flow you have to go through. But the idea is, I mean, as we've seen here, well, just to answer your second question, mapping these functions onto threads. So obviously, I can create something that's got more functional blocks here than we have threads to execute it on. That mapping function is done by the behavioral compiler step, which was in that stack. So if you recall, it's got an understanding of application level functional blocks. It's got an understanding of the parameters of those blocks in terms of their functions and timing. And it has an understanding of how to deploy onto the platform. So those are the key sort of 3 interfaces. And the whole idea of this is to avoid the situation in which the application developer needs to understand that we have a multi-processing platform with 2 tiles and 8 threads per tile. They just need to understand that we deliver, a level of performance and in particular a level of timing determinism.
So from the developer's point of view, you don't care if there's 8 processing elements. It's irrelevant. You just build the application that you want, and the rest is taken care of internally.
In principle, yes. I mean, I guess the one qualifier I would say, because that sounds a bit like magic, doesn't it? But obviously, if you run out of resources on the chip, you run out of resources on the chip.
Okay, but say it
the
like this then. This will decide, okay, one processing element is going to be an I2S effective hardware block,
Mhm.
and that's all it does. Another process element might be this audio chain, which at 800 megahertz can probably handle, quite a sequence of
Yeah,
EQ and things like that. And another element might be the, input side, whatever it may be, some PCM input or something like that.
exactly right. Yeah,
Yeah.
yeah, and I think the key thing you identified there is, where there are elements that are relatively, low performance or they're not particularly demanding, you can group them together on a single hardware resource, underlying hardware resource. But again, that all of those decisions are within the gift of the behavioral compiler. There is, but that doesn't get placed into the application domain because that would be platform specific knowledge that we're trying to avoid having to the customer and the user to be able to understand.
And so this concept where you might have multi-core processors, where you have to
Mm-hmm.
deal with an inter-processor calls, where somehow you shuffle things backwards and forwards between, that doesn't exist because they're not actually different cores. Is that
It does
something?
exist. That's a good question. It doesn't. There are two ways of doing it within xCORE. I'm sure there's more actually, but within a tile, you can actually share. There is a memory space that is shared, so you can actually communicate via memory. Between tiles, you have to communicate via an inbuilt switch. So we again, it's a level of detail that we would not expect our customers to have to understand, but you can do either, and in fact, you can use that switch-based communication to communicate between chips on a board as well if you want to, and it just looks the same. So you can build systems that way. If you want to operate, on the same level, same data from different blocks, you can do so within the same memory on a single tile.
Okay, and then the chip is mentioned. This contains the older chip, 500
Mm,
kilobytes, and you have 1 megabyte.
yeah.
But you also have external RAM.
Yes. Yeah. I mean, you can. So you can use an external DDR. Most of our customers don't. We sort of pride ourselves on our ability to be a sort of a single chip solution.
Okay.
But you can, if you wish, go off chip to memory. I mean, and this is a sort of, I guess, a good example of the xCORE philosophy. If you want to use SDRAM, you can deploy a software SDRAM interface in the same way you can deploy a software I2S interface or USB interface. You can, we do hardware and software. That's what we do.
Okay, and then how would that memory be shared between processing cores? Is that a detail you don't need to think about?
It's so again, we have libraries of, for example, DMA like components.
Okay.
That's a sort of an somewhat application specific question, but yes, you can have effectively a server, memory server. We have the ability to trap on memory addresses and go and get memory from Ethernet if you want to. So there are many different. The beauty of managing much of this in software is that you can add a significant amount of flexibility and security and system level specifics that are denied you by the fact that many things are delivered in hardware on ARM-based SoCs, for example.
Yeah, it's got a little bit hard to get your head around initially, but even a memory controller just becomes a software component.
That's right. Yeah, we have caches that are software components, and that's kind of interesting because then your replacement algorithm can be application specific. So, those kinds of things are, they're if you can implement them in software, you can do some some clever and value adding things that hardware implementations deny you.
It's fascinating.
It's very cool.
All right. Okay, I think we've delved pretty deeply into this. So yeah, Mark, thank you so much. We'll put some links below so people can find out more. And yeah, encourage everybody to like, subscribe, share, all that good stuff. And we'll see you all in the next episode. Thank you, guys.
Thanks, David. Thanks, Simon. It's a pleasure.